Jen Mora is a hydraulics engineer for Federal Highway, Western Federal Lands, out of Vancouver, Washington. And she worked with Oregon DOT before joining Federal Lands. And she investigates, supports, and promotes bioengineered solutions and effective fish passage design and best practices. She'll be talking about bedform evolution and bank importance in AOP culverts. And it's a subject near and dear to my heart because when I build these, I try to build stuff that moves and rearranged but doesn't disappear. And so maybe she has some secrets for us.
Okay. Hello. Thank you for your patience. Let's get this party started. Okay. So, hello. My name is Jen Mora, and I'm a hydraulics engineer with Federal Highways. I'm here to share with you the progress that we've made on the bedform evolution and bank importance and aquatic organism passage culvert study. So this study is a collaboration of work by Western Federal Lands Highway Division Office, based out of Vancouver, Washington, and the Turner Fairbanks Highway Research Center at the J. Sterling's Hydraulic Research Lab. This study was spearheaded by Sven Leon, an FHWA seasoned veteran and longtime NHEC attendee and contributor, and he's getting ready to retire, so I just wanted to take a quick second to celebrate his work and many contributions. Also, special big thanks and appreciation to everyone at the lab, Cornell, Hao-Yen, Nathan, James, and Zhao Ding, for their hard work and continued support of this effort. They really do amazing work. And this is a famous FHWA disclaimer slide that we've all come to know and love, and so just, friendly reminder that items discussed in this presentation don't reflect FHWA and DOT policy. You know the spiel. Okay, and then this is just a quick slide kind of going over terminology and definitions that will be included in the presentation. The biggest ones are like Western Federal Lands and stuff that you've all been in contact with, but just a quick overview. Okay, so what are we discussing today? So I'd like to start with a quick overview of what we'll be discussing. So we'll start with background information and a few examples of field observations that informed the need to investigate bedform evolution in AOP culverts and constructed AOP elements. We'll discuss study objectives, walk through preliminary experiments performed at the Turner Fairbanks lab used to inform design of the experimental flume. We'll go over the fabricated flume design and the features. We'll discuss bedform scans and preliminary CFD results, go over a quick summary of points discussed before going into next steps, future studies, another round of thank yous, and time for questions. Okay, so background. It's really fortunate that we got to go over after the monitoring protocol presentation because a lot of what informed this research is based on field observations. So field observations really informed the need to investigate constructed bed features and AOP structures. Similar to what Justin was discussing, current design methods utilize constructed interior banks or extensive fixed structures that often need or necessitate larger span culverts. And this is usually with the goal of achieving stream simulation. So field observations found that often these banks get washed out after a few regular flood events, which can, in some situations, contribute to a plain bed morphology and shallow expanded flow condition in the structure compared to the natural stream. So depending on the system, these conditions can lead to a potential decline in the quality and effectiveness of aquatic organism passage and structures. And so here what we have, these are photos of culverts constructed with interior banks. The spray painted line represents the height of the constructed banks that have now washed out. And so in the first photo, we see a low flow entrained along the culvert walls and boulder clusters through the center line. And then the photo on the right shows a washed out banks and plain bed morphology through the structure. Other field observations, so similarly, rigid structures such as rock weirs that are often used as grade controls or coarse bedding were observed to transform into potential barriers for passage due to jump height as bed forms naturally evolve around large rigid features. And these are a few examples of that. Okay, so what do we want to do with this study? The objective of this study is to investigate the evolution of bed forms in or near AOP structures to evaluate the effectiveness of aquatic organism passage. And so how? We want to do this by recreating constructed stream beds and AOP structures to evaluate how these bed form features evolve or devolve over time. Why? We want to do this in order to investigate, do desirable bed forms naturally evolve inside AOP structures? Are there potential negative impacts to requiring the costly construction of banks and fixed bed forms, or excessively sized culverts that can result in potential barriers to passage? And finally, for what? Why is this important? So the significance or the desirable outcome of this study is to develop documentation and really to facilitate conversations, mostly with resource agencies and partners on the effectiveness of current AOP design methods and best practices to inform future design. So when we talk about studying the evolution of bed forms in or near structures, it's in the context of the stream and the stream's characteristic features, understanding that these bed forms are critical to passage. So knowing this, we set up preliminary experiments that were set up to test if bed forms matching bed forms in natural streams could form from typical graded stream bed material by varying flow rates over time. And so the results of this preliminary experiment were used to inform the design considerations for our fabricated flume, which I hope you've all had an opportunity to play with in the lab this week. And so these are just kind of a few examples of the bed forms that we see in natural streams: plain bed, riffle, boulder sills, and boulder clusters. So it was important in the preliminary experiments that the test material used in this context has the same gradation and characteristics of a study site. So a typical graded stream bed material, composed mainly of gravels, cobbles, boulders, and sand, is seen in the photo on the right, was from 3 different sites in Alaska, was used to inform the gradation for the preliminary study. The typical graded stream bed material, again composed of gravels, cobbles, boulders, and sand, was scaled down to the dimensions of the experimental flume. So the figure on the left is a gradation curve of the mix used in the preliminary experiment, and this typical stream bed material is characterized by a gradation coefficient of 3 and D50 about 1/3 of an inch. And the photo on the right is a photo of the typical stream bed material that was scaled down and used in the experiments. Okay. So preliminary experiments were performed at the Turner Fairbanks lab using typical stream bed gradation. Were set up using different initial conditions. So this is an example of constructed banks with large roughness features along the culvert centerline. And the video, which should have played, and this is and the flow in the video was a max flow, what we determined for these prelim experiments to be the max flow, which is about 70% of the pump power that we had in those situations. And you could see the material kind of shifting over time. And we would do quick checks on depth, velocity, etc. This is another kind of example of prelim experiments. This configuration is no banks with large roughness features. And so the flow in this video is about a medium flow, so approximately 30% of the pump power. Using a little stone to kind of gauge velocities through bed forms. Okay, so what was the outcome of these prelim experiments? Overall, desirable bed forms matching the natural streams as seen in the figures were found to evolve from prelim experiment configurations using this typical graded stream bed material by varying flow rates over time. And so these are the examples we discussed previously that include plain bed, riffles, boulder sills, and boulder clusters. And so the results from this preliminary flume were used to inform the design considerations in the construction of the experimental flume. So this is an early rendition of the final flume design by Turner Fairbanks Lab, and it was fabricated to be mobile and easily adjustable with the goal of studying bed forms and different AOP design features for a range of site conditions. The overall length of the flume is 80.83 inches, as seen on the right from a top view, and it's designed to have three 24-inch sections for the upstream, culvert, and downstream configurations. General dimensions of the flume through the top are shown on the left, with internal cross sections that are 16 inches wide and 10 inches tall. And so the final flume, again, was fabricated to be adjustable and easy modified to test the different conditions. And so the configuration is characterized by a variable flow rate up to a max flow rate of 35 gallons per minute, a variable slope, an adjustable, which is adjustable from 0 to 17.5%, and easy to switch out gradation, and adjustable sections for the upstream, culvert, and downstream. This image is a top view of the culvert flume, if you didn't get a chance to see it, and it's to better illustrate the configuration and adjustable sections. And the goal with this is to have the sections ranging from bank full for upstream and downstream sections to 2 times bank full width for the culvert section, which is consistent with current design practice. And so these sections are made of plexiglass inserts, which can be modified to study other constructed features like baffles and sediment retention sills inside AOP structures. The flume has a flow spreader at the inlet and plastic and plexiglass retention screen at the outlet. Okay, and so an important aspect of this analysis is to couple these physical experiments with CFD simulations to better evaluate flow conditions through bed forms. So a laser point scanner was used to scan bed forms and experimental flumes to recreate flume bathymetries and CFD simulations. So the preliminary CFD simulations were performed to inform the overall experimental design. So on the left is a video of the laser pointer scanner used at the lab to scan bed forms. In the middle is a photo of the stream bed material in the experimental flume and a CFD domain on the far right. And so the nice thing about the point cloud light scanner is that it allows for greater resolution and granularity in the CFD domain, better defining the flow boundaries and conditions in the system. So this slide shows a process of getting the CFD domain surface from the 3D point cloud captured by the scanner. So on the left, we have the prototype photo of the bed in the flume. The middle graphic is a CFD reconstruction model using the point cloud data. And on the right, we have the domain with and without the mesh. So the picture on the right, on the top right is the domain with the mesh, where the CFD model divides the surface into tiny little cells where the flow parameters were calculated. And so the mesh is turned on the top and the mesh is turned off on the bottom. And so as you can see in the mesh, it's very, very fine, making it hard to really identify these cells at this resolution. So CFD models allowed us to analyze the flow fields very precisely. And so in these simulations, they were used to take a snapshot of the bathymetry, which is fixed, introduce a flow or a storm event, and look at the flow characteristics to evaluate performance factors as bed forms evolve in the structures. So these graphics capture the results for the bed shear stress for 2 different flow conditions, 2 liters per second on the left and 4 liters per second on the right, using the same slope 3% and the same bed form surface. So we can see bed shear stress values for the low flow rate range from 0 to 5 pascals compared to 0 to 10 on the right for higher flow rate, with a concentration of shear stress at the back at the outlet. Okay, these are results that show how the CFD model can be used to compare velocity distributions for different scenarios or flow conditions. So the graphic on the left is for instantaneous velocity distribution at a flow rate of 2 liters per second compared to the 4 liters per second on the right. And these graphics show that 3 sections were cut perpendicular to flow to visualize the instantaneous velocity solution for depth of flow all the way through to the surface. And there's also a slice cut at 4.2 centimeter elevation to capture the instantaneous velocities at the approximate midpoint of flow for each scenario. And you can see that the flow distributions are captured around bed form features. here in cross-section 2, where the rocks are not captured in the flow field results. And the results are consistent with expectations in that we have higher velocities for the higher flow rate. Okay, so in summary, preliminary flume experiments were successful in recreating constructed bed features and looking at the evolution of desirable bed forms, matching natural streams by varying flow rates over time. An adjustable culvert flume was fabricated to study typical AOP design elements and evolution of bed forms and AOP structures. The CFD simulations were successful in reconstructing the scanned bed forms and helping us evaluate flow characteristics. So where do we go from here? So next steps are to move forward with physical experiments and numerical modeling to evaluate the effectiveness of passage based on the analysis of these performance factors as bed forms evolve. There's interest in looking at different gradations, like typical stream bed gradation, extreme bimodal gradation, and uniform gradation, and also constructed interior features like banks, no banks, banks with rock queers, etc., as a few examples. Experiments will look at different flow conditions, low flow, bank full up to 75% of the maximum culvert capacity, for example, and will evaluate different performance factors. And so, in completing these experiments, we would also develop documentation and facilitate conversations with regulators and agencies, partners on the effectiveness of current AOP design elements and best practices to inform future design methods. And so while one of the desirable outcomes of this study is to develop documentation on the effectiveness of current AOP constructed elements, another one is to really kind of get the conversation going and partner up and find collaborators with other researchers and agencies to further study bedform evolution and the effectiveness of current AOP methods. And one possibility of this, of future research, is to couple the results, the CFD simulation results from this study with a fish path simulation model created by Oregon National Lab. So the fish path simulation seen in this video models the movement of fish based on flow conditions, geometry of culvert, bed forms, and fish behavior. So elements of data from this study can be used to define the criteria for each cell to better define how a fish will make it through the flow field, in addition to kind of capturing information on time and energy expenditures. So thank you for listening. Thank you to the lab. We're really glad to be here. Any questions?
Will you go through, or maybe they have, like the exercise of, the way they have to scale physical models, so you can go from your numerical results at this scale up to real world. Is that part of this work?
Well, we're actually scaling. So we have, we took study sites and scaled it down. And so.
And so, do you think at the end of this, you might be able to have the real design guidance to say that if you want these forms to show up, use materials of this size or that size?
Well, I don't think that'll be an outcome of this study specifically, but I think that the goal is to develop documentation and get the ball moving in that direction to be able to have more data to really come up with like data-driven solutions and guidance.
You had mentioned that grade control features have the potential to develop into barriers within those structures. Has there been any research on different shapes or types of barriers that are huge, baffles or piers or things that could be incorporated that would become less of a barrier perspective?
Well, that's what we're looking to investigate, and also it's a lot that it's not only the design, it's also construction, that making sure that a lot of these elements are buried enough and how they're placed, and so yeah, that is something that we're looking to like investigate.
How come you used only 1 foot wide flume to do this study?
So one of the goals and kind of driving factors in the design of the flume was to make sure that it's transportable so that we can bring it to conferences, that we can, and so it had to be kind of scaled down to a size that made that more easy. Just because the larger the flume, then the larger the pump, the larger the basin to collect water, the more sediment, and so just that becomes a big challenge. But because one of the driving forces behind the development of this kind of study was to engage others in conversations and have a physical experiment to kind of show things that we see in the field, so that we can get more on the same page of what is actually happening, then it was important to kind of scale it down to a size that makes it easier to transport.
So you were not like concerned about wall effects and things like with having like such a narrow, such a limited, let's say, distance over which like feature would be, especially relative to the size of the segment that would be used. Or maybe that's the future.
Yeah, I think it's the flume. I mean, there are a lot of variables to consider, and the flume can't capture everything. So it is something that we're exploring with the lab, like which experiments make sense in this kind of smaller scaled flume, and what would make sense in a larger kind of, in a larger setup. Mm-hmm.